Hello, we're the team of the Hegel seminar called Knots. And in our seminar, we're dealing with knots that are tritangentless, so they roll if you put them on an even plane. And we are trying to numerically find tritangentless knots that roll especially well. Our work is based on this family of tritangentless knots created by H.R. Morton, but to possibly find knots that roll even better than the best rolling Morton knot, we introduced two new parameters. One is this Z scaling parameter that just stretches out the Z component of each knot, and the other one you can see in the denominator of the coordinate.
And of course, we then also need a function to minimize, and we consider the center of mass of a Morton knot, which is due to its symmetry at the center. And the idea is that the center rises and falls as the knot rolls across a flat surface. So the smaller this vertical variation, then the less energy needs to be transferred between kinetic and potential. And one possibility is to just calculate the vertical variation and then just add the lateral component. But another possibility, maybe a bit more sophisticated, is to calculate the translational velocity of the center of mass in the direction of rolling. And you can see the plot of the one where we calculated the velocity of the center of mass. And in the next slide, you can see the plot of the first idea, so where we just added the lateral component. And as you can see, we tend to have very little A and Z parameters.
Yeah. And after we had these plots, we decided to look in the optimal regions for potential candidates of knots which roll even better by optimizing in 2 and 3 parameters respectively. Unfortunately, the global optimum in the 2-parameter case doesn't really exist. The knots tend to get better by degenerating in a cylindrical-like form, basically a thin needle, and stretch out infinitely. This improves the knot behavior significantly, and it's the only major way to optimize the lateral and the vertical displacement. However, cases can be found which are not completely unrecognizable, which still have better qualities for rolling than the initial results by Stephen. So here we have the baseline knot on the left, which has a transversal displacement of 32%, and one of the next best candidates has a 20% transversal displacement, which is already a bit better. And as you can see, the knot is quite similar, but it gets a bit flatter and a bit elongated. Continuing in this trend, we can see a further result from following this result pattern, and it's very stretched, very thin, but has pretty much a halved transversal displacement compared to the last one, and a very, very minimal vertical displacement. Our success with the 3 parameters was not very minimal. Basically, the third parameter doesn't really help. It can only make the results worse. Unless you start with very bad 2-dimensional results, then change in the third parameter can lend some value, but not very much. And here are the 4-dimensional plots of the 2 objective functions. They are a bit tough to see, but as you can see, a change, especially here, a change in the third parameter doesn't really affect the quality of the values. And now we'll show you some videos of the models we produced.